Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll start a new session. Last time we ended with the first part of logical agents, which is mainly was about the propositional logic, representing knowledge bases using propositional logic. The second part will be similar, but we will use first order logic. Okay, so that's another way of representing sentences in the knowledge base. Why we need something else other than propositional logic? Actually, propositional logic is really simple. That's a good thing, but it only assumes that the world contains facts. It doesn't see the world as we see it in natural language. In natural language, we used to talk about objects. We used to say that some objects have relations together. Okay, we cannot do that in propositional logic. So generally, propositional logic has very limited expressive power. Another example of limitation in propositional logic is the sentence that you see on the slide here. If I want to say that pits cause breezes in adjacent squares, I have to list a sentence for every square. So I say for square 1, breezes, pits can cause breezes. Square 2, pits cause breezes in these specific squares, and so on. Okay, so that's too much, of course, if I just want to say that generally pits cause breezes in adjacent squares. So I can do that in first order logic, as you will see inshallah later in this lecture or next lecture. So first order logic assumes that the world contains three entities or three types of entities. The first thing is objects, like people, houses, chairs, colors, monitors. Okay, all of these are objects that we talk about in reality, in real life. Okay, boards, things like that, food, desks, all of these are objects. But life doesn't have only objects, it has relations between objects, like prime, like brother of, like bigger than. Okay, so these things are called the relations. It relates objects together. Sometimes the relations are about one object, like round, so whether an object is round or not, that's a relation with one object. We call it a unary relation because it has just one object, and sometimes also we call it a property. Okay, and there is a special case of functions or of relations called functions. Okay, so a function like further of, it takes one object or more and refers back to an object, a unique object. Okay, so father of a person, of father of Ahmed is Ibrahim. Okay, so it's still a relation between Ahmed and Ibrahim. I can look at it as a relation, but it's a special case of a relation because it takes one or more objects and refers back to one unique object. Okay, best friend, one more than, plus, all of these are functions. Okay, because they take one or more objects and return back one object, one unique object. Okay, for this combination of inputs or input objects. Okay, so in first order logic, we will play with three types of elements: objects, relations, and functions. And we'll see that with these three, in addition to some of the connectives and some elements in the syntax, we will express much more sentences or much more in much more or much easier way than propositional logic. Examples: 1 plus 2 equals 3. So that's a sentence, right? That's a full sentence. Now I can see inside this sentence that 1 is an object, 2 is another object, 3 is a fourth object, is a third object, sorry. Okay, so we have, these are three objects. We can also see that 1 plus 2 is an object also, right? Because it represents 3, right? In semantics. So that's another object. So we have actually 4 objects in this sentence. 1, 2, 3, and 1 plus 2. How about relations? What are the relations that we have in this sentence? We have equals. Okay, so equals relates 2 objects together, okay, and says that these 2 objects are the same. So we can see that equals is a binary relation. Okay, it relates 2 objects. This is one, sorry, and that's another, and says whether these 2 objects are the same or not. Okay, we also have functions here. Where is the function here? Where is that function here? This is the plus. So plus is a function that takes 2 objects and refers back to one object that is, in that case, is the summation of, or the addition of, these 2 objects. Okay, so in this very simple sentence, we had 4 objects, we have 1 relation, and we have 1 function. Here's another example. Squares neighboring the compass are smelly. Squares neighboring the compass are smelly. Where are the objects, where are the relations, and where are the functions in this sentence? Anyone? Faisal? We have 3 objects: squares, compass, and smelly is an object. Where is that? No, red was a relation. Yes. Okay, so smelly is not an object. So squares and compass are objects. Okay, anything else? Smelly is a relation. So one by one, Faisal. Smelly is a relation. What type of relation? Is it unary, binary? Unary. Okay, so something is smelly. It's a relation of one object. It takes one object. Okay, so smelly is a relation. So let me write here. So the square is an object, and compass is an object, and smelly is a relation. What else? Is there any more relations? So neighboring is a relation or a function? That doesn't make a lot of sense, Faisal. Okay, neighboring here is a relation between 2 things. This thing is a neighbor of that thing. Okay, remember always what is the difference between a relation and function. That's maybe a bit confusing. Think of a function that will only return one thing, and it cannot return for the same input more than one thing. Okay, so neighboring here cannot be a function, because for one object it can be a neighbor of more than one object, right? So it will not return all of these. So neighboring here is a relation. It takes 2 objects and says that whether these 2 objects are neighbors to each other or not. Okay, is that clear now, Faisal? Okay, so neighboring here is also a function. Sorry, a relation. And what type of relation is that, Faisal? It is a binary relation because it relates 2 objects. How about functions, Faisal? Yes. Yes, so we don't have functions in this sentence. Okay? Thanks, Faisal. Any questions about this? Okay, let's take a third hypothetical example, which is in your textbook. Let me tell you the story behind this example, and then I will ask you about what are the objects, what are the relations, and what are the functions. We have a person called Richard. Okay, this person is a brother of another person whose name is John, and John is also a king. Okay, John has a crown on his head and also has a left leg. Of course, it has a right leg, but the right leg is not part of the story here, just the left leg. Okay, so John has a left leg, and also Richard has a left leg. Okay, so that's the story behind this figure. Okay, now let's think together what are the objects, what are the relations, and what are the functions, if any. Let's start with objects. What are the objects that we have here in this story? Anyone? Someone other than Faisal, please. Yusuf? Wa alaikum assalam wa rahmatullahi wa barakatuh. A crown and two, يعني you liked the two left legs before the persons? Okay, so the persons, yes, I would like to say they call them by names better than just person, because person is just a general thing. So we have Richard is an object, John is an object, and their left legs are objects, and also the crown is an object. Okay, so we have 5 objects here. Thanks, Yusuf. How about relations? How about relations? Someone other than Yusuf and Faisal. How about Mubarak? Mubarak, are you with us? Mubarak. Mubarak? Why you don't? You cannot open mic? طيب سعيد. سعيد. Saeed, are you with us? طيب محمد فوزان. وعليكم السلام ورحمة الله وبركاته. Okay, so on head is a relation. Okay, and what type of relations is that? I mean, is it unary, binary, ternary? Binary. Very good. Okay. What else? So where is the relation then? Yes, brother is the relation. So what you said is the example of using the relation, not the relation itself. Okay, so you should say just brother is a relation, and what type of relation is that? Binary again. Okay, so brother of x and y means x is a brother of y. Okay, what else? So has a left leg is a relation, and do you think it's a relation or function? So if we said that has left leg, it looks like a relation, but we can see it as a function also, right? Yes, because it refers to the left leg of that person. So that's a function. So I can say that this is a function. Okay. And what else? Do we have other relations? How about person? Is that a relation? Is an object? Okay, so this is unary relation. And if I say that um, undergraduate student, this is a property, right? A property of a person. So this is a unary relation. It's a relation, but it's a special case of a relation which is unary, which is a relation about one object only. Okay? Yes, yes, exactly. So a person is a relation of R. I mean of any object. It can be true or false, of course. Of course, if I said person of R, it will be true. If I say person of crown, it will be false. Okay, so yeah, so person is also a relation. And what else? Sorry, king is another relation, yes, which will be true for John but false for Richard. And what else? How about crown? Okay, that's very similar to also person, Muhammad. Okay, so the crown itself is the crown of John itself is an object, but crown by itself is a property. يعني I can say that it's a property of that crown. It can be a property of another crown, right? So is crown, if you think of it that way, is a relation that takes only one object. So it's again unary relation. So actually we have two binary relations which are brother and what else? On head. Okay, and we have I think three. Did I say unary or binary? So these are binary relations, brother and on head, and we have I think three unary relations: person, king, and crown, and we have one function which is left leg. Okay, anything else, Muhammad? Sorry, what's that? The stuff they are. Ah, that's the okay. We didn't say anything about it in the story, so yeah, it's just an indication that he's a king. He has money. Okay. Yes. Okay. Thanks, Muhammad. Faisal, do you have a question? Yes. What do you mean by plus here? Mm-hmm. No, a crown. I don't see it that way, Faisal. Crown. How can crown give you an object? You mean on head gives you an object? Okay. Yes, but the function always returns one thing that is unique. But I can say on head, and I can say on head, hair, if he has hair, and Hussein مثلا. And I can also say that on head, which is true, right? I can say also on head, crown, and Hussein. If that's the case, then on head cannot be a function that takes Hussein, that takes a person, because now it returns two things. Function doesn't return two things; it returns just one object. Okay, so it depends on the semantics. I can see why you are confused, and I understand that. It depends on the semantics of the word that you are trying to represent here. Okay, if that's the semantics of the word tells you that, or tell you that there's only one thing on the head of a person, then okay, yes, you can refer to that by a function. The function will return whatever is on the head of that person. Okay, but if that's not the case, then it's a relation. And remember, a function is actually a special case of a relation. So it's a relation, but it's a special case because it always returns one unique object, and it refers to an object. It doesn't give you a truth value. The function doesn't have true or false. Okay, the function is referring to an object. You can think of it as a name, a way of naming an object. Okay, that's the difference between a function and the relation. Is it clear now, Faisal? Okay. Yes, because it returns the object that is the left head of that person. You can, if you don't want to represent legs or left legs as objects, then you can think of it as a property. Has, but in this case it will be has left leg. Okay, something like that. So you can. No, here in this story, in this worldlet, the left leg is an object. Yani the person is an object, and its left leg is an object by itself. Okay, it's a bit weird here, yani hypothetical, but that's the case in this story. Exactly. Yes. Okay. Any more questions? Okay, now let's talk about the syntax of the first order logic. We have in the syntax multiple elements. We have constants, and the constants refer to objects like King John, like 2, like QU. These are constants, and the constants are kind of names of objects. We have also predicates, and the predicates are the representation of relations. Okay, so brother is a predicate, greater than is a predicate, person is a predicate, and so on. Okay. Okay. So this is the second element, second type of elements in the syntax. We have also functions like square root, left leg off, and so on. We also have variables, as we saw in propositional logic. We have here variables x, y, a, b, and so on. And these variables will refer to objects. Okay, but they can change the value of them. The value of a variable can change. Okay, it refers to at some point it refers also, of course, to one object. Usually we use we write the capital initials for constants, predicates, and functions, and for variables we use small letters. We also have connectives, which are the operations that we already used in propositional logic, which are not, implies, and, or, and equivalent. We have the equality element, which means that whatever is on the left hand side refers to the same object that is referred to by the right hand side. Okay, so the equality here means that these two objects are the same. And when I say 1 plus 2 equals 3, that means that 1 plus 2 refers to the same object that is referred to by 3. Or when I say the president of US equals Trump, so that president of US is referring to the same object as Trump. Okay, so that's equality. And quantifiers, for all and there exist, I think you are familiar with that, and we'll talk about them inshallah later today. So these are the basic elements. Let's see how we will form sentences out of these basic elements. First, we'll talk about what we call a term. A term is the thing in the syntax of first order logic that refers to an object. Okay, so we have three ways to refer to objects in first order logic? Constant, variable, or a function? Constant, variable, or a function. So constant like US, variable like X, function like president of. Okay, so that we have three ways of referring to objects. There is also atomic sentence, okay, atomic sentence, which is one of two ways. So these are the simplest. When we say atomic sentence, what we mean actually is the simplest sentences in the language. Okay, we have it in two ways: either a predicate, which refers to a relation, like the one that is at the bottom here, brother King John and Richard the Lionheart. Okay, so brother King John and Richard the Lionheart means that's the semantic of it, or the interpretation of it, or the meaning of it. King John is a brother of Richard the Lionheart. So that's a sentence by itself, but that's a simple sentence. Okay, it's a predicate. Remember, the predicate refers to a relation. Okay, and we call it a relation in the world, in the real world, but in first order logic we call it a predicate. We represent it by a predicate. Predicate is a relation that takes multiple objects, which are referred to here by term 1, term 2, up to a term n. Okay, so that's one way of looking at a simple or atomic sentence. Another way is the equality sentence, which is term 1 equal term 2, which we already mentioned in the previous slide. It means that the object referred to by term 1 is the same as the object that is referred to by term 2 here. Okay, so these are the same object. So this is a sentence and that's a sentence. Okay, so here an example is president, as we mentioned it on the previous slide, president of US is equal to Trump. So now US is a constant, Trump is a constant, president of is a function. Now this as a whole refers to an object, and this refers to an object, and equal here means that these two objects are the same, and that's a sentence. Okay, another example of a sentence is a predicate like that, like the one at the bottom here, greater than length of leg of Richard and length of left leg of King John. So that's a sentence. What is the interpretation of that sentence? The interpretation is that the length of the first leg of the length of the left leg of Richard is greater than the length of the left leg of King John. Okay, so that's another sentence. So these are the ways in which we represent sentences in first order logic. We use terms refer to objects, and using these terms we use them in predicates or in equality sentences. Okay, now we can compose complex sentences out of these atomic sentences. How? By the connectives that we all know about. So if I have a sentence S, I can create another sentence, not S. I can, if I have two sentences, S1 and S2, I can connect them by and, or implies, or equivalent, and I will get a new sentence, which is now complex because it has inside it is composed of atomic sentences. And of course, the complex sentences can be connected also using these connectives to create more complex sentences. So here are examples. Sibling King John and Richard implies sibling Richard and King John. So that's a complex sentence. Why is that? Because this is by itself is an atomic sentence that says that King John is sibling of Richard, and that's an atomic sentence that says that Richard is a sibling of King John, and that's as a whole now it's a complex sentence. It's another sentence that says that if King John is a sibling of Richard, then Richard is a sibling of King John. Okay, Of course, I can also connect with or and. Here I connect two predicates, so that's a predicate. One, which means one is greater than two. Of course, that's false, but it's still a predicate. Remember, a predicate is a relation that is true or false. Okay, or another predicate which is less than or equal to 1, 2, which means 1 is less than or equal to 2. So this one is true, of course. This one is false, which means that the whole sentence is true. Similarly, we can have the similar thing with and. So we have here 1 is greater than 2 and not 1 is greater than 2. Of course, this is false because this part is false. Okay. Any questions up to this point? Questions? Okay. Now let's talk more about truth in first order logic. We kind of touched upon that already in the lecture, but let's make it clear now. Sentences are true with respect to a model and interpretation. As we said, to know the truth value of a sentence, we need to know what is the model that we are talking about and what is the interpretation of the elements, what is the interpretation of the predicates, what's the interpretation of the functions, and so on. Models, of course, contain objects and the relations between them. The constant symbols refers to objects, the predicate refer to relations, and the functions refer to functional relations. If I have a predicate like that, like this one, in general, this predicate is true if the objects referred to by these terms are actually in this relation in reality. Okay, yani this atomic sentence is true if and only if the objects referred to by term 1, term 2, and term n are in the relation referred to by the predicate. Yani this is true if it is semantically true. It depends on the interpretation. Okay, and it depends on whether these terms actually have this kind of relations between them or not. Okay, so it's not just by the syntax. It has, of course, we need to check the semantics of the elements of the language. Now we'll talk about two quantifiers, the universal quantifier and the existential quantifier. I know that you are familiar with that already, again from the discrete math course, but let's make it clear here because we will depend on that for the next lectures, inshallah. So the first one is the universal quantifier, and just to remind you, these are parts of the first order language also. Okay, so we didn't talk about them earlier, but they are part of the language. As we said, constants, variables, predicates, quantifiers, and so on. This list of 6 or 7 things, among them are the quantifiers. So what do we mean by this kind of sentence? For all variables, of course, that's the syntax of it. For all, some variables and then some specific sentence. So if I say for all x p, that means that this sentence is true in a specific model M if and only if p is true for every x. So if and only if p is true, with x being each possible object in the model. So for every x in the model, in the worldlet, p is true. If that's the case, then this whole sentence is true. Let's see an example. If I want to say everyone at QU is smart. Everyone at QU is smart. Okay? How can I say that using for all? Here is how. For all x, if x is at QU, because that's the condition here, right? Then this x, or this person, of course I'm here, the domain is persons, and that person will be smart. Okay, so that's how we write this sentence in first order logic. Everyone at QU is smart. We can write it that way. For all x at xQU, which means, we have to say which means, right? That's the interpretation of it. X is at QU. So if x is at QU, that's the condition, then the conclusion is x is smart. If I want to say this in propositional logic, then I have to say it for every person in the world. Okay, so Ahmed, if Ahmed is at QU, then Ahmed is smart. If Mona is at QU, then Mona is smart. If Abdul Hamid is at QU, then Abdul Hamid is smart, and so on. Okay, so of course that will be very exhaustive. In first order logic, I don't need to say anything like that. I just say if for all x, if x is at QU, then x is smart. Now there is a common mistake. There is a common mistake that you should avoid when you deal with for all. Sometimes we tend to use and as the main connective instead of implies. So let's look at this example. For all x at xQU and smart x, or in other words, x is at QU and x is smart. Is that the same like saying that everyone at QU is smart? Are these two things the same? What do you think? They are not the same, Faisal. Why is that? Okay. So if I give you this sentence, Faisal, and I told you to just interpret it in natural language, how would you write it? Yes, very good. So everyone is at QU and everyone is smart. That's the interpretation of this sentence. If it's true, of course. Okay? But this sentence is not like this, of course. So this means that everyone in the world is at QU and everyone in the world is smart. Okay? That's different from saying everyone at QU, so that's kind of a condition here, is smart. So whoever is at QU is smart. Okay, so that's different. These two things are of course different. How can we interpret this? Using first order logic? Back here, we have to use the implication statement. Okay, if x is at QU, then x is smart. Okay, is this clear? The difference between the two sentences is clear. Any questions about that? Okay. So now let's switch to existential quantification. So we use there exist and some variables and then sentence. That means that this sentence as a whole is true in a model M if and only if P, which is the sentence here, is true for at least one object in the domain, in the model. At least one. So if there's at least one that satisfies P, then this whole sentence is true. Because basically I'm saying there is someone who is this. Okay, so if there is at least one who satisfies this predicate or sentence P, then the existential sentence is true. Example, someone at QU is smart. Someone at QU is smart. Now you might think that we should do it that way. There exists X at XQU implies smart. Is that the interpretation that has the same interpretation? When can this be true? When can this sentence be true? If I say there exists X such that if X is at QU, then X is smart. This sentence can be true if there is at least one, if any person in the world is not at QU. Right? Because this is P now. Sorry. That's P now. So when can be, if P is true for any X, then the whole sentence is true. When can this be true? If this part is false, if the condition is false, right? You know from the implication. If this is false, then we don't care about the condition, then this will be true. So that means that if one person in the world is not at QU, then this whole sentence is true. Of course, that's not what we want to say here with someone at QU is smart. So that's not the right sentence here. Okay, the right one is there exists X at XQU, which means X at QU and smart. So that means that there is at least one person who is at QU and smart, which is the same like this sentence. Someone at QU is smart. Okay. Of course, if I want to say this sentence in propositional logic, I have to have a disjunction of sentences for every person in the world in that model. Okay, so I have to say Ahmed at QU and smart, and Ahmed is smart, or Mona is at QU and Mona is smart, and so on. Okay, so that's of course very easy to say using existential quantifier. And as I said, it's another common mistake to avoid is to use the implication instead of and with the existential. Okay, so that's the example that we saw in the previous slide. There exists X such that X is at QU implies X is smart. Of course, that's true if there is anyone who is not at QU, regardless of being smart or not. And this is, of course, not what we want here. Okay. Any questions? Okay. Now let's talk about more properties of quantifiers. So if I have two quantifiers like that, for all x, for all y, this is the same as for all x, for all y. So we can switch the order of the variables here, as long as we have both of them to be the same. Okay, same as there exists. So we can say there exists x, there exists y. That's the same as there exists y, there exists x. But if we have two different quantifiers, switching them is not the same. So for all x, for all there exists x for all y is not the same as for all y there exists x. And here's an example. If I say there exists x for all y loves xy, so x loves y. Okay, so what does that mean? What does that mean? If I want to interpret this sentence in natural language, how can I write it? Anyone? In natural language, how can I write this in natural language? Yusuf? In natural language, Yani, when you talk to someone, you say there is an X. In natural language, how would you say it? You don't use variables in natural language, right? What is the interpretation? No, you don't say X and Y, of course. What is the interpretation of there exist and for all in natural language? Yes, so say it that way. Not sum of X, Yusuf. Okay, you are saying X again. Yani. I'm trying to get rid of X and Y. So you can say someone, right? You don't have to say X. Yani. When you talk to your brother, you say, brother, X went to. You don't say that. Look, there is X that played football yesterday. You don't say that. Okay, you say there is someone who played football yesterday, right? So, and you say all played football yesterday. Okay, so how can we do it that way here? Yes, very good. Someone, there is a person, okay, or someone who loves everyone in the world. Right? So that's the interpretation of this. Okay, now how about the other one, Yusuf? If we switch it, the quantifiers, everyone, yes, everyone loves someone. Everyone in the world, and not loves, is loved by, because Y here is the first one. Okay, so everyone in the world is loved by someone. Okay, if we put, yeah, by someone means at least someone. Right? By some someone can be one or more يعني زي ما انت بتقول كده yes بس يعني the point here is that these two sentences are not the same. يعني there is a person who loves everyone in the world. That's not, of course, the same meaning as everyone in the world is loved by at least one person or by someone. Right? These two are not the same. And that's what we are saying here. We're saying that switching these two quantifiers is not correct. Okay, so there exists X for all Y is not for all Y there exists X. Okay, so pay attention to that. Also, we can, of course, as you know, we can represent one quantifier using the other, okay, using De Morgan laws. So for all X, for example, for all X, X likes ice cream, we can say that there's nobody who doesn't like ice cream. Okay, so for all X likes X ice cream is equivalent to not there exists X not likes X and ice cream. Okay, how do we get that? It's like this: for all X P, this is equivalent to double negations, right? I can say double negation for all X P. Right? Now, by De Morgan law, double negation of for all P is there exists not P, which is the same here, right? This is not, and that's there exists, and that's not P. Okay? And similarly, the other way, there exists X likes X and Berkeley. So there is someone who likes Berkeley in the world, I hope. And then I can say that not everyone doesn't, not everyone in the world doesn't like Berkeley. Okay, same thing. Okay, do you have any questions on this? Okay, if that's the case, then we'll stop here. And inshallah talk to you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.